With that, let's move on to the next section of our presentations here today, and it's our panel discussion. We have a number of people that are going to be on the panel today. You can see them all pictured there, and I'd like to start introducing them to you so we can move on to the questions. And the purpose of this panel discussion is to get some of those live questions from customers and the real world questions, and have a discussion about them and really understand what's going on there. So let us start introducing the panel to you. First people that are on the panel is Thomas Arnspach Young, and he is out of our York office. Tom has spent a bit of time as an application specialist for us, and he's written a number of articles. He has a bachelor's in engineering and electronic engineering from the University of York, and he handles a lot of inbound questions from customers. Thank you for joining us, Tom. Next person on the panel is Jeremy Govier, principal engineer out of our Tucson, Arizona office. Jeremy's had over 23 years experience with Edmund and in the imaging world. And his job is really to connect customer applications to design and manufacturability of the products that we make. Has a degree in optical engineering and a real good background of making all those connections to make the products really work effectively and correctly for the customer base. Next person on our panel, Katie Schwartz. Senior design engineer, specializing in both optical design and optomechanical design. She holds an MS in optical sciences from the University of Arizona and a BS in optics from the University of Rochester. She's authored a number of articles and even some things in some books, and is a member of the SPIE Board of Directors. Thank you for joining us, Katie. Three more people that are on the panel. Nick Sischka, who you've seen quite a bit of today. Again, he's the sales operations manager for imaging here at Edmund out of the United States. And he's got a degree in optical engineering and is kind of our guru on sensor technology and sensor capabilities. Rhiannon Jenkins, she has the distinction of spending time in three of our offices, our York, UK office, our Tucson, Arizona office, where she spent time at the University of Arizona getting her master's degree in optical sciences. She is a project manager and spends a lot of time working on the engineering and developing of both custom and standard products for Edmund. She works out of our German office now in Mainz, Germany, and spends a lot of time dealing with customers and application spaces. And then finally, the last member of the panel, I'll be handing the mic over to somebody else to run this section. I'll be on the panel as well. You know about me already. So with that, I'm going to ask Boris to come back on the floor. He is going to take over the controls here. And Boris is going to spend time asking us questions that have come in from our customers. Boris is the manager of our imaging group in Europe, does a lot on our business development side. He has a PhD in physics and has authored numerous articles and done many presentations on imaging and other science and technology areas. Boris, over to you.
Thank you so much, Greg. Very excited to do this here today for you. I also want to give a special thank you out to the people that supported us with the questions. We had a lot coming in and we had to make a few hard decisions on which ones to pick. And a special thank you also to these guys who recorded even videos that we will play here in a short moment of time. We also have questions that we have just prepared on the slide. So moving on, jumping directly into it with the first question. This came in from Stefan Hartmann at SIG, and I'm just going to read it out. I'm looking for a solution in the macro range, somewhere between 1x and 5x. When I can't find a suitable macro lens, I often use a fixed focal length the other way around. And now there's two questions to it. A, what are actually the implications in terms of optical performance when flipping a lens around? And B, is that still a viable option today, or is there something better that could be done? And regarding that first question, the A part, I'll kick that over to Jeremy.
Okay. So this is something that historically has been done a lot in the early days of machine vision. And there are a lot of implications to the image quality. I'm not going to get into the details of things like how aberration and diffraction get affected by this. We touch on those kind of things later on in some of the demos Nick's going to do. But the main thing, and one of the simpler ones to understand, is how this affects magnification and how that's going to affect your overall performance of your lens. So, and for example, if you have a lens that you can get to work at 1/4x and you want to use that closer, get a higher magnification, when you flip that, you're going to take the inverse of the magnification. You're switching your image and your object distances. So you go from a 1/4x to a 4x magnification. Some of the good things about that is going to be when you're changing to this positive magnification, this higher magnification than 1, you're going to have a much larger image. And this was particularly good in the early days of machine vision when photographic lenses were used a lot as your lenses for your system. And the reason for that is when you blow up that image by switching the magnification around, now your image from your lens is much larger than your sensor. So you're really only using the very center of your image on your sensor now. If you have that example of a 4x magnification, now your image is going to be 4 times larger than the sensor it was designed for. So you're using just the center. And in the early days, when we're using photographic lenses, they were really designed to perform very well in the center, where typically you would put your subject, you know, a face, something like that. And they didn't have performance in the corners. Machine vision, we often care as much or maybe even more about what's going on at the edges of the image than we do the actual center of it. So being able to use just the center portion of the image all the way across your sensor is a really nice advantage when you do this flipping of the lens. However, there is another trade-off with the magnification that has a downside for you. If that lens was producing a blur, you know, the best spot it could get at, let's pick a number, 5 microns in size. And if you're using a 5 micron pixel, that works great when you're using it initially. When you've flipped it around though, that magnification also magnifies your blur. So that 5 micron blur becomes a 20 micron blur, which now may be 4 times as large as your pixels. So you can lose a lot in your resolution and your lens may no longer be pixel limited for you. So it's a trade-off you get. And again, to those early days when this was used a lot, that wasn't as big of a deal because often the pixel sizes were larger than what the lenses were capable of doing. We were sensor limited. Nowadays with these 20 megapixel sensors we were just talking about in the last demo, that's usually not the case. We are lens limited, or what the performance is usually limited by the lens. So you're going to start to get this lack of resolution. You're not going to get the most out of your pixels when you do this kind of a flip often. It'll still be an improvement. You're getting, if you went from this 1/4x to 4x, you're seeing 1/16 of your image. Your object has now gotten much smaller, but you are still getting 4 times the resolution. So it's an improvement of 4 for your resolution, but you're costing you 16 times the field of view. So it is a loss of what you're going to get.
All right, thank you so much, Jeremy. Let's also talk quickly about that part B of that question. Tom?
Yeah, sure. Thanks, Boris. So I think it used to, like Jeremy said, it used to be a fairly good option in the early days of machine vision, but not so much anymore due to the type of sensor we see today, really the typically larger sensors with smaller pixel sizes. When it comes to alternatives to these flipped fixed focal length lenses, there are many lenses that are actually macros, but they're just not branded with the word macro. 3 types of lenses that I could think of where this is the case are telecentrics, variable magnification lenses, line scan lenses as well. And out of those 3, I would say that the telecentric lenses are probably the best alternative to flip fixed focal length lenses. Besides having the advantages that come with telecentricity, so low distortion, no perspective error, telecentrics have a few other advantages. So mainly wide variety of mags to choose, so lots of different options in terms of magnification, and many different options as well that cover different sensor sizes. So you can get telecentric lenses that focuses more on the smaller sensor sizes, so 1/3 inch, 1/2 inch, 1/1.8, and then all the way up to the bigger full frame sensors as well. But then some downsides to telecentric lenses is they typically have fixed working distances, although small changes in working distance can be achieved quite easily often. Another factor to consider is the size of these lenses, especially for the lower magnifications or the ones designed for larger sensors. Then if you have a space constraint application, then this is really going to be a problem. And often, because the lens is bigger, then you're going to see an increase in cost as well.
Yeah, quite valid points. Valid. Does anyone else on the panel have some thoughts they want to share here?
Yeah, just really quickly, just talking about implications with flipping lenses. One of the things that can also come up when you're doing that is, as Jeremy mentioned, you're obviously taking something that should be like this in object space, and now you're doing the same thing in image space, and yet you're trying to fit it onto what is likely the same size sensor. And so that can introduce a lot of stray light into the system, and it can, that manifests itself most typically as kind of like a almost like a bright spot in the center of your image is kind of how that can manifest itself. And so just looking out for ways to deal with that with either a special coating on the barrel or you know, say flock paper even can sometimes help with that if you're trying to set something up in the lab, because stray light can become an issue as well.
All right, thank you, Nick. Anyone else? Also looking at the time, I think we should move on to our second question, and this came in by video. So I'll mute, let's roll it.
Dear Edmund Optics team, my name is Jonas Schulz and I'm a research fellow at the Technical University of Kaiserslautern in Germany. My question is regarding the depth of field. I noticed that for telecentric lenses, this is often called out in the datasheet. But for fixed focal length lenses, this is often not the case. Why is that? And what is the logic behind this specification? Thank you very much.
Yeah, that's a great question. Thanks, Jonas, for sending us this by video. Let's see. Rhiannon, you want to have a go?
Sure, thanks, Boris. Just before answering the question, let's do a very, very quick primer on depth of field. We already talked about it a little bit today. Professor Jenner spoke about it a little bit, but it's a depth within the image space that has a specific resolution achieved. So there's a couple of things that you have to define when you're talking about that. One of them is what your resolution limit is when you put a bracket around that, because if you have a very low resolution, then your depth of field can grow a lot, or it can be a lot smaller if you have a very high resolution. There might only be a single kind of plane in the field where it makes sense to talk about achieving that resolution. Another thing to talk about is the difference then between a telecentric lens and a normal lens. You can consider a telecentric lens as something that it has a fixed magnification across the whole of its working distance, or wherever it's used. And then most often for a telecentric lens, there is also a specific working distance that you're working at. And the depth of field, after you've specified a resolution, it does still vary a lot with the working distance or with the magnification. So when you're working with a telecentric lens, you've got a specific magnification that is always true for the system. And then the depth of field makes sense for that magnification. And you can narrow down the parameter of what the resolution is that you're interested in. And then it makes sense actually to talk about or to have a specific specification to say this is the depth of field. When you're talking about a fixed focal length lens, as you vary the working distance, your magnification is going to vary a lot because your field of view is going to vary. If you're close, you're going to have a much higher magnification compared to if you're looking to a very big scene at a large working distance. So what you have to be careful about is that not only do you have to specify then this resolution or minimum resolution that you're going to accept as defining your depth of field, you're also looking at a lens that a customer could be using at, I don't know, say for example, 50 millimeters all the way out to infinity. So then what does that specification really mean in reality? And it's certainly something that you can figure out, and it's something that can be calculated, but it's just going to vary a lot depending on the application space. So if you have a specific application, you can give us the details of what you're looking at, then we can talk specifically about what that really looks like or what it really means within an application.
I absolutely agree with that statement. Yeah, absolutely. All right, I'll open that question up for anyone else here on the floor. Additional comments?
Yeah, I wanted to hop in too, because whenever we end up talking about depth of field, I wanted to point out that a lot of times people use DOF as a kind of an abbreviation for that. But we talk about both depth of field and depth of focus in imaging applications. So, I just want to point out that if you're reading about the depth of field or depth of focus where you see the abbreviation DOF, you definitely want to kind of think critically about what context it's being used in. So the depth of field is related to your object space. It's talking about in front of your lens in the working distance. Your depth of focus is going to be at your image plane, the depth of focus over the allowable resolution for your system. So just wanted to point in, it's something to keep in mind, whether you're talking about object space or image space, is depth of field or depth of focus.
True point. I think everyone who's starting fresh in the machine vision and imaging environment, there's one conclusion everyone draws very quickly, and that is that nomenclature is not well defined at all.
Yeah, it's not really standard, and they are related. I mean, the magnification of the lens does allow you to move from depth of field to depth of focus, so they are related by the magnification. But agreed, it does trip people up.
Yeah, absolutely. I remember when I started with this, it was very frustrating for me. I will be honest with you here. All right. Any other comments on this, gang?
Just really briefly echoing that I still mix them up quite often. That and faster F number, slower F number, higher F number, lower F number, and how those are backwards.
It's not just new people.
So I still get it mixed up quite often. One other thing too, quickly, is that if you're using a design software like Zmax or Code 5, and Katie and Jeremy definitely jump in here if you know something that I don't hear, but those two softwares, to my knowledge, don't actually have the ability to spit out depth of field curves as they're written. So you have to either flip the lens around, or you have to write a macro to do that for you, because they're not going to by stock be able to kick out a depth of field curve. So if you're looking in those softwares, that they can put out depth of focus curves, but not depth of field.
Yeah, we usually look at a through focus MTF and look at the depth of focus, but that's what I mentioned. Yeah, so you can write a macro, or if you have specific spatial frequencies, you can kind of back calculate based on magnification. But agreed, right. It's so for any of the developers out there, give us a nice built-in depth of field analysis.
All right, that's a message. Let's keep on moving. Let's jump to question number 3. We're not going away from this topic too far. We'll still stick around the environment between entocentric or fixed focal length lenses and telecentric lenses. Give me just a second to adjust my screen here. All right, so I'm just going to read it out now. This came in from Robert Schäfer from EMS Tech, and he's asking, in which cases do I really have to use a telecentric lens? And under what circumstances could I really get away with just using a normal fixed focal length lens? Let's see, Nick?
Sure, yeah, I can take this one. That's no problem. Thanks, Robert, for the question. So there are definitely applications where you would want to use a telecentric, and only a telecentric might work. But there are also places where maybe you can't fit it in your system. Telecentric lenses can get really large, and they can sometimes be unwieldy depending on what you're trying to look at. For those unfamiliar, if you're trying to look at a particularly sized object, the telecentric lens is going to vary in diameter based upon that. So if you're trying to look at something that's very small, your lens diameter can be small. But if you're trying to look at something large, your lens diameter has to scale up commensurately associated with that. So they can be tough, especially if you're retrofitting a system, or if you kind of didn't really take into account the envelope that a telecentric lens can take up. And so oftentimes you can be forced to say, well, can I make do with a fixed focal length lens? And the question is yes, sometimes. Generally speaking, the advantage that a telecentric lens is going to give you is repeatability and higher accuracy. If you have a long enough fixed focal length lens with low enough distortion, and you can have a large enough working distance there, then generally speaking, you can do some accurate measurement with fixed focal length lenses. The big thing that can kind of throw that off there is the repeatability that you have with respect to object placement with the lens. And so because your magnification is going to change as your working distance changes with a fixed focal length lens, that means that the distances that you're measuring are going to change. And so with a fixed focal length lens, if you can repeatedly put that object in front of the lens every single time, you know that the working distance is going to be exactly the same, you know you have your distortion calibrated out and you don't have to worry about a ton of parallax error, then you can definitely use fixed focal length lenses for measurement, right? Because generally speaking, telecentrics are going to be used for that measurement where you're trying to do some very fine gauging. The advantage that the telecentrics have there is that if your object moves slightly, right? Let's say your objects are on a conveyor belt and they're coming along being presented to a particular lens, then there might be some positional uncertainty there. A telecentric is not going to change the measurement that you're going to get outputted because of the telecentric nature of the lens, where a fixed focal length lens would.
Well understood. Thank you so much, Nick. Again, I'll open that question up to the entire floor for additional comments.
Yeah, I was thinking about this in terms of not just the lens that you need, but also the illumination. We definitely have a lot of applications that we see where not just a telecentric lens is important, but also a telecentric illuminator. And the classic example is when you're trying to look at the profile of a 3D object and see the projection of it. Most often you see kind of screw inspection, or maybe catalytic converters. That's another really classic example where you really want to see a clean profile of the shape of the object that you're looking at. And the object has some 3D depth to it that you don't want to disturb the image. So that's kind of the parallax error that Nick was talking about, that can really have an impact. And when you use telecentric illumination as well as a telecentric lens, that's when you get that really clean, sharp profile image that isn't affected by like maybe some light shadow on the side, or you don't quite see like a clean outline of what you're trying to measure. And that's where we would recommend not just a lens, but also the illuminator to go with it.
Yeah, absolutely agreed here too. Anyone else? Although I'm actually looking at the time, so I'll just propose to keep moving on here and jump right into our question number 4. So if you can pull that up, I'm also going to read it out for you. We're now moving over to, we actually touched on this a couple of times during today's event in the keynote, but also during these small question and answer sessions after these imaging labs. So it's related to F-mount and optomechanical design, I guess. So Katie, I guess I'll kick that over to you, but I'll read it out first. Just a bit of a heads up here. When choosing optics for line scan applications, one is usually limited to F-mount, M42 or similar mounts. 2 questions to it. A, F-mount often proves to be not robust enough. Is there a good workaround for this? And B, is there a new mount coming up for line scan lenses that is both robust but also standardized, especially regarding the flange distance? Yeah. A big thank you to Michael Stelzel from MST Vision for that question. And as I said, Katie, you want to have a go?
Sure. Yeah. So, you know, F-mounts aren't exactly our favorite mount for industrial applications and imaging applications. So the F-mount, if you're not familiar with it, is a bayonet style mount that was really developed by Nikon for SLR photography cameras. So if you do photography, they're very convenient. It's kind of a spring-loaded, you turn and snap the mount on. So it's really convenient for what it was intended for. However, the kind of question indicates it's not exactly the most robust mount when you're talking about an imaging lens system that is highly sensitive to alignment. And if you have anything exposed to environment or vibration or shock, really spring-loaded connection is really not your ideal, rigid connection that you'd like. And then there's issues with the flange distance. I mean, F-mount has a very long flange distance. The M42 that was mentioned doesn't have a standard flange distance. So, you know, we really prefer to go to something that's more of a rigid connection with a shorter and more standard type of flange distance. One thing, so you did mention earlier, is the TFL mount. And the TFL mount is nice. That's designed for right around the 28 millimeter sensor size. And you can think of it as a larger C mount. It has an M35 threading, and it has the same flange distance as a C mount, the 17.526 millimeter flange distance. So that really allows you to go to a larger format sensor than something like a C mount, which isn't really going to work for your line scan or larger format sensor. So that the TFL mount is nice. You can also look at something like going to an M58 or an M72. That's also an option, but all of those have a threaded connection where you're rigidly mounted up against a flange. And that's really what we'd like to see for more industrial style applications. In terms of what's coming out in the future, I think I'll probably hand that off to Greg, if you can speak to that, since he's often the one having direct conversations about what's coming down the pipeline, so we can make sure we're doing the right design for the market.
Yeah, and it's an interesting question because Katie touched on the TFL, which is now becoming more accepted in industry, and the M58 and M72, and that really covers a lot of range. Really what it gets down to is the complexity of, you want to make the smallest camera footprint possible with the best resolution and the most optical capability matching it. And there's trade-offs for putting things in between. GIA a few years ago, it's the Japanese Industrial Imaging Association, put together a set of standards for sensor sizes and the mounts that could be used. When they did that development effort, I think they came up with about 112 or 120 different possible mounts that existed on the market already. Many of them bayonet, but a lot of them the thread end types. And what they tried to do is limit it down to a few per the sensor range size that was going to be there. My feeling is that you might see a few things coming out, but really it's going to be to these thread type mounts, probably tucked into the TFL M58 and M72, covering most sensor capabilities that are out there. I don't foresee anything truly new coming onto the market, though it might be plausible. But it's really that a lot of things already exist, and people are trying to stick with those things to reduce the complexity of how many different optical designs have to be done and how many different adapters and cameras are going to be on the market.
I'd like to add a little bit to something Katie mentioned there about the flange distance and the importance of that, and why the F-mount can be tricky from the optical design standpoint and drive the design in ways that we don't necessarily like. Because that was designed for an SLR camera, which had to have that reflex mirror in the path. There's a very long distance from our flange to the image plane. And that forces a lot of things in our optical design. When we have shorter focal length lenses, the lenses want to get closer to the sensor just naturally. But it also means the further away we take those lenses, when we have large image planes, which typically is what we're going to have when we look at these larger mounts, and fast lenses, or in other words, really large aperture lenses, it means that the lenses need to get very large if they're far away, because you've got a cone, you know, because that large aperture, you're driving the lenses to be larger, when if they get closer to the image plane, they don't have to be as large. And that can really be a big constraint in our design and drive a lot of the things in the optics if we have to artificially push our lenses further up than they want to be. So by having a flange that's close to the image plane, it gives the lens design more freedom to where we actually put the lenses, and we aren't artificially putting constraints on that are going to make things either perform worse or be more complicated and expensive than they need to be.
Yeah, that's a good point.
Yeah. Said another way, you end up with the largest, most expensive lens that you can make, and it doesn't perform to the desired level at the same. It's a very frustrating thing when we're in.
All right. Thank you, everyone, for these answers and insights. Let's move on. We'll look at question number 5. This comes in from Andre at Dices Medical, and he has sent us a video. So I'll mute again and let's roll that.
Hi, this is Andre from Dices Medical. I was wondering if you could explain how to differentiate between chromatic aberration and aliasing effects when dealing with color artifacts and color sensors. Thanks.
All right. Jeremy, how about you?
Okay. This is a really interesting problem, and one that is a little bit hard to just talk about without pictures, but luckily we do have some demos coming up shortly that get into explaining more about what we mean by the color aberration and what that looks like. But what we're really talking about is generally what we call lateral color. That's usually what you're going to see, and you see it in your image as a banding of colors, or your blue light going to one place and everything else going to another. So you get this kind of blue-yellow band when you have lateral color in your design. And that's an aberration that we are often trying to fight in our lens design. And then in the aliasing, because your pixels are made up of these filter, this moire filter, or on top of the sensor, you can end up with each pixel being a little bit shifted, the blue from the red, from the green being slightly shifted, and you'll see this banding of color around an object as well from that. And both can look similar. The biggest difference, though, is the pixel effect happens all across your image, and it happens the same way across your image. So at the center of your image, depending on where your edge is, you can see this blue or red or green around it, but it happens anywhere in your image. While lateral color is what we call a field-dependent aberration. So it gets worse the further away you are from the center. So you can generally see lateral color at the corners of your field, but you will never see it in the center of your field. So if what you're seeing happens in the middle of the field, you're just seeing this aliasing effect from the moire pattern on the sensor. But if you're seeing it in the corners, then you're more likely seeing lateral color. And also with the lateral color, it always happens away from the center. So you'll typically see a blue line towards the corner and a yellow towards the center, regardless if that's in the top right-hand corner, the bottom left-hand corner, it's going to always be that same directionality to it. And typically what you do see is that blue-yellow, because you get the blue going the furthest away, and then everything else, or the absence of blue, which gives you a yellow on the nearer side. While the pixel problem, you kind of can see red, green, or blue on your image.
And just quickly, shameless plug, we're going to be talking about chromatic aberration in one of the upcoming labs. So we're going to be talking about it on monochrome cameras, not on color cameras, so you won't be able to see the actual color, but you will be able to see the blurs that come from that. So make sure to stay tuned for that, because it's going to be kind of cool.
All right, we got a few minutes left. Anyone wants to say something on that question? If not, I'd like to go to the next one, which is then question number 6. Again, I'm going to read this out for you guys. So it came in from Marco at Data Logic. What is the best way to estimate the MTF performance loss between nominal MTF and as-built MTF where manufacturing tolerances are considered? I think this is a very good question. Thank you, Marco. I'm really curious to hear all of your answers here. Let me check. Tom, you've been silent. Go.
Yeah, sure. So I'd just like to thank Marco for that question first. And before really getting into the answer, I think it might be quite good to explain what is meant by nominal MTF and as-built MTF. So nominal MTF is the MTF you typically see in a data sheet. It's the theoretical curve where manufacturing tolerancing isn't considered. And as-built MTF is the MTF you can expect after manufacturing tolerancing has been taken into account. There's no really straightforward way to determine MTF loss between nominal and as-built. There's no kind of blanket formula that can be used to determine this that is applicable to every lens. So tolerancing plays a major part in accurately simulating this MTF loss. Something to also consider is that F number and wavelength have a significant influence on the amount of loss between nominal and as-built MTF. I have a couple of tips that I'd like to share that can be used to get a general idea of what you can expect from a lens when looking at nominal MTF and looking at a nominal MTF curve. These aren't absolutes, but more general guidelines on what to expect. So generally, slower f numbers, such as your, for example, f over 5.6 or f over 8, will be less sensitive to tolerancing than faster f numbers like f over 1.8 or f over 2.8, and therefore less MTF performance losses to be expected. And my second tip would be that it's usually safe to assume that if nominal contrast, so that's the MTF that you see in your data sheets, is at 20% or more at a given frequency, it will usually be good enough for most imaging applications.
Yeah, that 20% is a number that is often, you hear that very often when you ask around and deal with different customers and different applications. So thanks again, Tom, for those tips. Anyone else want to have a go here?
Yeah, I definitely want to hop in from a design perspective. You know, Tom talked about you know, looking at data sheets. So if you're a customer purchasing something from a company like us, you know, you don't have access to all the manufacturing tolerances. So I think using rough rules of thumb, I mean, I think it's really important to understand that kind of 20% number definitely comes with a whole lot of caveats in terms of, you know, the wavelength and like Thomas mentioned, the F number. But if you're developing a lens, or you're working with us on developing a lens, or you're doing in-house design, I mean, really the way that you go about this is usually doing a Monte Carlo analysis. So if you're the one determining, you know, your manufacturing tolerances and designing the lens, a Monte Carlo analysis is a statistical simulation of basically different distributions of tolerances. And it allows you to just get a rough idea or a predictive statistical idea of what your yields might be. A simpler way to go about that, it's not as robust as a Monte Carlo, but is doing something called a sensitivity analysis. And that's where we just look at the individual tolerances up for an element or a system and see how that affects your MTF performance. And that can give you a rough idea of where your trouble spots are going to be, what elements or what assembly tolerances are really going to cause you the most headaches when you're trying to get your best MTF performance. So just from that side, you know, how would it, if I were anything from the design side, how would you look at your as built versus nominal? You can go about that, and some of the design codes have built-in analyses and built-in optimizations for you know, optimizing your yield as opposed to your nominal performance, because the as-built system is really what's going to happen in reality. So that's really what we care about looking at.
If I can add to that, I think it's also important to mention that during the design phase, when we're developing a lens, be that if it's something for the catalog or custom, the optical designer puts almost the same amount of time and energy into doing tolerancing of the design as we do into optimizing it. Mm-hmm. And what typically people think of as the design, it's the amount of effort we do into tolerancing is very high. And the reason for that is it's a lot of statistics. We can't give a MTF curve to say, this is the as-built performance, because it's a statistical distribution. We usually are looking at, depending on the lens, the number of surfaces, how its optomechanics are, hundreds of lines of code of things that are being perturbed or changed from its nominal when we do a tolerancing run. Everything from the thicknesses of lenses, their radii, where they're positioned in space, all of these kinds of things add into these tolerances. And the only way of looking at that is statistically, looking at Monte Carlos. If we just moved everything in one direction, added them all up, nothing would ever work. It's just too many variables that are involved in it. So you have to look at it statistically, which takes a lot of effort. And it also usually means we're looking at this at a finite number of data points. So when we do an analysis, we do it to usually a spec of a resolution and contrast across the field. So We'll say something like, we need to make sure this lens meets a 20% contrast at 145 line pairs throughout the field. And we're doing our analysis to make sure that lens will yield to that. But that's different than giving an MTF curve. An MTF curve is going to have hundreds of those points of frequencies in contrast that we're looking at. And trying to statistically say, this is the curve that it will meet is nearly impossible. So that's why what's presented is always the nominal curve. And then often there'll be a specification that the lens is guaranteed to meet, like 145 line pairs, 20% contrast at a data point, is because the statistics that's involved, and also the testing when we test our lenses to ensure they're meeting that before they get packaged and sent out to you, we're testing generally at a frequency and a contrast value.
I think that there's something important to take away from all of this. As a customer, knowing that it's a complex thing is important to understand. But I think what the real takeaway is that you need to be able to ask the questions and be able to get the answers for the particular product and the way you're going to use it. No, not all 35mm lenses behave the same. Not all lenses in the same product family designed to go with a specific sensor behave the same way at similar F numbers or wavelengths. That there's complexities to this. As applications get more advanced and the pressure on getting the highest level of performance continues to rise in systems, I would encourage you to reach out and ask those questions. And we should be able to explain why things work the way they do and why we would choose one lens over another. And very oftentimes, we will recommend a lens that might have a slightly lower nominal MTF because we know the as-built design for the particular application is going to perform better than the one that might have the better general purpose MTF at that one data point that's able to be shown. So just keep that in the back of your mind and ask the questions. We should be able to answer them for you.
Thank you very much, everyone. That was a very, very good discussion. I really appreciate it a lot. We're a bit over time here, so I say we will conclude our panel discussion for now. I want to give a few big thank yous. First of all, to our customers sending us these questions. That's already very much appreciated. And then, of course, I'd like to thank everyone here on the panel. And then there's the last but very special thank you to Jeremy and Katie, working out of our Tucson office in Arizona. And I think you're 9 hours behind us. So thank you so much for joining us at this point in time. That's all that I had to say. Back to you, Greg.